Hi. Very good afternoon to the class. So basically, today is our first class. I can see that most of you have already joined the class. So according to my list, basically there are 31 students in this class, including Paul Junwen, who is from the RTE. So the rest is from the IEE 3, if I'm not mistaken. So may I know who is the class rep in this IEE?
Hello, sir. I'm Chie.
Oh, Chie is the class rep, yeah?
Yeah.
Chie. So later, can you form a WhatsApp group including all our students so that if we have any questions, then we can post at the WhatsApp group. That should
Okay.
be
Yeah,
easier.
sure.
Yeah, thank you. So good morning, good afternoon to everyone. So sorry, just now you are yelling, right? Yeah, Yao Ting, Long Yao Ting. Okay, so good afternoon to Long Yao Ting. So this is our first class, except that for the group number one, we have already attended the tutorial class. So basically, for today, we are going to start our first lecture. But before that, let me introduce myself. Okay, so my name is Hong Kai Si. So this is my handphone number, and this will be my email address. And I have the following academic qualifications. Okay, so I'm a chartered engineer, professional technologist. Also, I've taught for 15 years, uh, about 15 years, and then I have 1.5 years of industrial experience at Intel Microelectronics spinning. So that's all about myself. So if you have any questions, so you can WhatsApp to me through this number 012-6194-239. So or if you need to send me an email, so you can send to this hongks@tasi.edu.my. So basically, before we start, let me explain about our assessment. So we will have one midterm test. Okay, one midterm test. After that, we will have one assignment. Okay, one assignment. The assignment will be 20%, and the midterm test will also be 20%. And then we have the final exam will be consisting of 4 questions. Then it will have 60%. Okay, so for our assignment, I would like you to form groups of 2 students. So one will be doing the Intel microprocessors. Another one will be doing for the other type of processors. Okay, so the assignment will be given to you later. Okay, so any question you want to ask before we start our lecture? If you have anything, you can feel free to turn on your mic. Oh, someone want to join? Can sing, eh? It's our students, right?
Yeah.
Yes, sir. Because his account is
Oh,
currently got some issue.
okay, sure. So we have 31 minus 3, so we have 28. So we still have another 3 haven't come yet. But never mind. So before that, let me explain to you. Basically, I will upload all the lectures and tutorials to our Google Classroom. I believe all of you have already joined the Google Classroom. But I only have 30 students. Who are the last one? Who haven't joined yet? Yeah, if you need to join, you just let me know, yeah? Okay, so all my lecture notes have been uploaded here. So you can see my lecture notes and also tutorials over here. For your information, I will only post the answers, solutions of your tutorials after I finish the tutorial, so that I can give you some time for you to do some exercise first. So these are basically the lecture notes that I will teach for this semester. There are 9 chapters. We will learn the performance, the instructions, the pipelining, cache memory, RAM, virtual memory, storage system, and also the input-output system. So there are totally of 5 tutorials. I have all the answers, but I will only give it to you after we have finished the tutorial class, so that you have the chance to do it yourself first. So this is the assignment. For the assignment, basically, I will ask you to study what are the improvements from the Intel old processors to the new processors. So this is the Intel X0X0. So you have to study the improvement until the Intel Core i7. Okay, as an improvement of X0X6. The other student in your group will need to do for other processors. I'm not. You can do any processors you want. For example, like the ARM processors, or you can do the mixed processor, any processor. Okay. So the assignment will be discussed maybe next week. So we discuss the assignment. Okay. So besides, if you are interested to do some assembly language, so I think got a little portion to do the assembly language if you want. Okay. So are you interested to do assembly language? Anyone? Are you interested to do assembly language, or you prefer to do the analysis only? Anyone? Never mind, I will just follow the last, perhaps. So definitely, if you want to understand the computer, you need to do the assembly language a lot. So, okay, later next week we'll discuss about this assignment. So, okay, now I will give you like a few minutes to discuss among yourself who you want to group with. In my list, there are 31 students. That's why I will allow the last group we consist of 3 students, only the last group. Okay. All the other groups will have 2 members. So any question? If not, then you can start to form your groups. I'll give you 5 minutes. 5 minutes. Yeah. For your information, I'm using 2 computers. So sometimes you see me appear here because the other computer is for me to show you the presentation. You can form a groups of 2. Okay, I see Chun Wei like to do assembly language, and also Chong Yi maybe, and also Yao Ting perhaps. So we try to learn a little bit assembly language, because without knowing how to do the programming, we do not understand the computer. Yeah. Okay, no. The yes is to answer your question that Kenson is our classmate or not. Okay, so okay, I understand that. So it's okay. Uh, so don't worry, Shunwei. Okay, I understand what you mean. Okay, I trust you all have already formed a group. So basically, I will start my lectures. Before I start my lectures, any question you would like to ask me? Any question you would like to ask before we start our lecture? You have already got all your timetable, right? So I think should be all right. The timetable, we have you have one tutorial for every 2 weeks, and then we have also two lectures class. Okay. So basically, let me check what are the class that's inside my timetable. Yeah. So let's confirm with you so that you won't miss my class. So basically, this is my timetable. Yes. Okay. So your friend from group one has already attended my tutorial on Monday. So for the group two, you will be attending on Wednesday. So now we have our lectures here, and also we have another lecture over here. So we have 2 hours of lecture today, and also another uh, 1 hour, 1 hour of the lectures on 2:30 p.m. On Friday. So every Friday and every Tuesday, we have the lecture class, 2 hours, 1 hour. So sometimes I will use some lectures hours to discuss a little bit example from the tutorials. But we have ample times to discuss about our lectures. We have 2 lectures to discuss 1 chapter. So don't worry about the time. So basically, for your information, last semester, this subject was taught by Ms. Yong. Okay, so I'm taking over from her, but I've taught this subject a few years ago, only a few years ago. So uh, so don't worry. Yeah. Okay, so basically, we are going to talk about our first chapter. The first chapter is about the fundamentals of the computer design. What is a computer? Computer is a very advanced technologies, right? So basically, computer have changed our modern human life, and then you will be able to do a lot of things with computers. So we want to learn what is the fundamental of the computers. So the fundamental of computer design. So why does this subject called B3213 computer architecture? Because it's to teach you how to design a computer. Okay, so that's why the first chapter will be about the computer design, and also we will learn how to measure the performance. So the fundamental of computer design, what is computer architecture? Computer architecture means you become the architect of a computer. You decide what is inside a computer, but before you can design, so you must know what are those things inside the computer. So the functional operation of the individual hardware unit within the computer system, and also the flow of information, and also the control inside the computer. So when we study computer architecture, we want to learn about the hardware organization. We want to see what are the hardware inside. Then we want to know what are the technology. I believe you are all have already learned about the digital electronics. We have all those technologies like CMOS, transistor to transistor level, all these or PMOS, and also NMOS. All these technologies will be used to design computer. And also we want to learn about the parallelism. Currently, we have many computers. Most of our computers actually have more than one processors, or at least it has more than one core for the current days. We have the Celeron processors, we have the mobile processors, and also we have Pentium. Last time we have Pentium, now we have i3, i5, i7. And also, you might not aware that we have i9, right? But that one will be very expensive. So you might not see in market often. So we also want to learn about the programming language interface. We want to know when we talk about this move A H, comma 4. Do you know what does it mean? It's actually moving this one into the AH. Okay, so you'll learn a little bit about this. Then we want to know the interface design, either through the applications, and also application means is the Microsoft Words or other apps. For example, all your apps and also all the programs. We also have the operating system. We want to learn a little bit about the operating system. Then we want to learn about the measurement and evaluation. There are two ways to do the measurements. So operating system, now we have Android. You like Android, right? Because you all, every day you use this Android all the times. I think every day, right? So after that, we have the Windows. Windows from Microsoft. And we also have other operating system, like from like BOS and also Linux, and also Unix. All those are the very important operating system. So OS means operating system. So we are talking about very deep level inside the computer. If you have any question when I talk about it, you can always turn on your mic and ask me question. So as a computer designer, let's say in future you want to become the computer architect, or you want to design a particular component inside computer. So what is your task of a computer designer? Let's say in future, you go to Intel to work as an engineer, or you go to Huawei. So you might need to do the functional requirement analysis. So the functional requirement analysis is when you design a computer, what type of function that you want to include for your computer. For example, you want to design the computer for your house, okay, for your for the home usage. Okay, so you might want to have different type of the function. So for scientific computing, for example, let's say if you want to run your computer to run MATLAB, AutoCAD, or etc. So you want it to have high performance floating point calculation capability. Okay, let's say you want it for the business people. You see, business people, they don't do integration. They don't want to know very complex mathematics. They only want to, mostly they want the plus, minus, multiply, divide, right? For the business people, mostly, yeah. Okay, so you might want to focus on all those functions. Or you want to do it for general purpose, so you have to have the balance between the performance for a range of tasks. So when Intel designed the processors for i3, i5, i7, it's basically for the general purpose, so that all of us can use it. Okay, so let's say it designed for the supercomputer is for the scientific computing. Okay, sometimes they design it for the business purpose. Okay. Second thing you want to think about is the level of software compatibility. When you design the computer, let's say you will need to design software as well, right? So your software, let's say I buy i3, okay, then I buy a Word, okay, I spend $1,000, okay. After that, a few years later, I want to upgrade to i7. Then if the company, the computer company tell me, I cannot reuse this Word software, I have to rebuy a new one, Word version 2 for another $2,000. So it will be very tough for me, right? I want all my software to be able to use it when I buy a new one. So the people look at the level of software compatibility. So for the performance level, if you have the software compatibility, so the computer is flexible, it does not need a new compiler, and there's no portability issue. Portability means your computer, the software can run at any of the computer. Okay. Also at the binary level, we have the Xd6 architecture. So this one is basically the Intel architecture. Intel Xd6 is a general purpose computer. So last time, when the computer was first invented, the model is called X0, X6. Then after that, we have X0, 2X6. Okay, and then X0, 3X6. Okay, and then X0, 4X6. After that, got the 5X6, but they don't want to call it 5X6. Why they don't want to call it 5X6? When I read from some of the books, the reason is why they don't want to use, they have another name called Pentium. Okay, the reason why they changed to Pentium, according to the source that I read, is because they found that the number cannot be patented. Okay, when they bring this X0, 4, X6, 5X6 to the patent company, they don't want to patent it. They said X0, 4, X6 is a number. Everyone can use it. How can you patent 4X6, right? I want to patent one, cannot, right? So that's why they changed it to Pentium. After that, they have the Pentium 2, okay, 3, 4, okay, etc. Now we have the i3, i5, and also i7. So what are the difference between all these things? And also we also have the mobile route and N series processors. What are the difference? The difference is how many cores, how many processors cores are inside. And also what is the number of cache. So for the OS requirement, we have the address issue. So we want to know what are the OS required for your computer. For example, for your handphone, you will need to use Android, right? Android is an OS mainly developed by Google. And then we have the Windows developed by Microsoft. There's some story because Google doesn't want to use the because they want to have their own operating system for the mobile devices. That's why they created this Android. But Android has been first developed by other company, so you can go and read a little bit. So also we want to know the conformance to standards. So what is the language? What are the languages that you can use? Like the C, a C language, or maybe Java. Last time we have Pascal. We have other programming language, and also we have the operating system, also network, also input output, and IEEE floating point standards. That IEEE has already designed how do you represent floating point using computer. Okay, any question before I continue? Any question? Are you still with me? Yeah. Yes, sir. Okay, good, very good. So, any question you want to ask me?
So
I'm still on. Yes.
What is floating point?
Floating point. Floating point means okay. Floating point. Floating point is the, for example, 1.1234 is the floating point. Yeah, floating point. Let's say integer is 36. You cannot have any decimal points. So this will be the floating point. May I know who is talking? Just now who is asking question? Oh,
Me,
Chong
Chumi.
Yi. Chong Yi, okay. Hi. I cannot see your name and my other computers to come here. Okay, hi Chong Yi is 1.1234. Okay, other question? If no, then we will continue. So don't worry, by the end of the first hour, I will give you 10 minutes to 15 minutes rest time. So in this chapter, mostly will be theory first. So now we want to talk about the computer system of the technology trend. In 1988, okay, 1988, we have the supercomputers. We have the MPP, massively parallel processors. Last time they talked about using multiple processors to create a computer. Then they also have the mini supercomputers. And then we have the mini computers, workstation, PCs. And then most of the people at that time, 1988, they might not, before that, they might not be able to buy computer because the computer was expensive. After 1988, when they created X0, X6, X02, X6, then people start to be able to buy computer. Only a few thousands, let's say 3,000 to 5,000, okay, per computer. But at that time, 3,000 to 5,000 is a bit expensive, okay. So after that, in 2002, we have the powerful PC and also SMP. SMP symmetrical multi-processor. So they have also the parallel processor. Okay, and then the network of SMP workstation. Also, we have the mainframes, supercomputer, and they start to talk about the embedded computers. What is the meaning of embedded computers? Embedded computers means the processor is inside any of the devices like your handphone. They start to talk about all these things starting from 2002. Then today, 2021, what are those things exist in our computer world? It's totally different already because we have a lot of embedded computers. We have computers inside all the washing machine. We have computers inside the television. We have computers inside all the inside aircons because they need to control certain things, right? So computers exist everywhere. Anything that has a processor is called a computer. And also we have the laptop. I believe all of you have a laptop. Most of you have a laptop, or who is using desktop at home with the camera, right? So I believe most of you have a laptop, right? Since you are joining my class. And then now the laptop is cheaper, a little bit cheaper, because 1,000 plus you can buy quite a decent one already. Of course, not the i3. i3 is 2,000 plus. The day I go and do some research, i5 expensive, i7 even expensive, and also we have an i9. Oh, this one very, very expensive. So you wait until a few years later, so it will become as cheap as all those things. And also we have the mobile processor. We have the Qualcomm. Okay, so Qualcomm for our Xiaomi handphone. Also we have the smartphones, also tablets. Okay, so all these are the current trend of computer. So you see the computer has exists everywhere. Okay, so let me explain to you why there is such change in 30 years. So performance-wise, the technology has been advanced. We have the Cmos technology. Cmos means complementary metal oxide semiconductor. And also, because previously, they only have the transistor. to transistor level logic. Okay, they only have the BJT, all those transistor. But after the invention of this CMOS, so because CMOS use very less power, so that's why in terms of cost and performance, CMOS has become better. And also the computer architecture advances, improve the low end. So we have started to use the RISC and pipelining, superscalar, and also RISC technology. What is this RISC? The RISC computer, basically, they are divided into two architecture. Okay, architecture. The first architecture, we call it CIS. And then the second architecture, we call it RISC. There is the argument long before. So from the very, very long time before. Okay, so the RISC, the CIS supporter is actually Intel. They have made a lot of instructions, many instructions, number of instructions, a lot. Okay, so that you can do many instructions. But RISC is actually supported by this arm, your handphone. The RISC say number of instructions a lot. So this one a very minimal instruction. Okay, that very primitive instruction. So that whenever you need to do anything, you need to use a lot of instruction. So the RISC technology has also made our handphone more advanced because our processor can be smaller. Okay, the price also become lower cost due to the simpler development. And also we have the CMOS VSI, we have the smaller system, also fewer components. Okay, and also because nowadays everyone is using computers, so the manufacturer can manufacture high volumes. That's why because of high volume, they can accept the low margin. Low margin means low profit, low profit margin by class of computer due to fewer services. So now, when your computer got problem, last time when our computer got problem, we go and send to the computer shop, please help to repair. But nowadays, people don't want to repair already, One spot, if no warranty, they will directly say, I want to buy a new one. Yeah, mostly, if not, then buy a second-hand one. If budget is a concern, if the cost is concerned, they will still buy a new one. They don't go and repair because the repair cost is a few hundreds, and the second-hand one also a few hundreds. So usually they don't send for repair. Yeah. So last one is the function. The function, we have the rise of the networking and also local interconnection technology. We have Wi-Fi now. I think currently at your home, you have Unify, you have massive broadband. So you seldom will connect through the cable, right? Yeah, the cable, no, right? So you connect using the Wi-Fi. So there is the advance in our technology. So you can see the growth in our microprocessor performance. The performance has been grown very, very exponential. Starting from this MIPS processor, IBM Power 1, Hewlett Package 9000, the Alpha, they go up and up and up. So you can see that the performance increased roughly 1.58 times per year. So it's very, very high improvement. Okay. So we also, besides the microprocessor, we also see the improvement in our RAM, the dynamic RAMs. You can see that the size of the RAM has been increased from 1978 until 64 megabits in 2001. Nowadays, what is our RAM size? My computer has 4 gigabyte, right? 4 giga. I believe some of you have 8 giga, and most of yeah. So because I'm using the N series computers, because I find that N series processor actually consume low power, so my computer does not need a fan. Okay, When you consume low power, then there is no fan. So when it's no fan, so no noise. That's very quiet for me. And then most important thing is very cheap. When I bought this computer, actually is 2 years ago, it spent me around 880 ringgit. Okay, 880 ringgit. The brand is HP. Okay, quite yeah, very worth it, right? Yeah. So it can do many functions. But of course, if you want to run MATLAB, you have to go to i5, i3, i5. Okay. Yeah. So this is the cost of the microprocessors. So you see that the cost always decrease. Last time when during 1990 something, the cost of a computer at least 3 to 5K in Malaysia ringgit. Around there, the normal one, you cannot seldom find 1,000 plus. Nowadays, you can find it, for example, like 2,021. If you want to buy N series computer, it's around, let's say 4,000 series. So it's around maybe less than 2K. Okay. If you want AMD processor, you can buy it for 1,500. Okay. So you can see that the cost of the processor has dropped, but the performance becomes higher. So I think the computer is one of the technologies that advanced so much in these 20, 30 years. Okay. So now, after we have talked about all these computers introduction, let me go to the a little bit about how do we measure the performance of the computer. So now we will go to the integrated circuit cost. What is an integrated circuit cost? So this is actually the IC, but we don't call it IC, we call it die. Okay, so in our factory, let's say Intel or any other factory that have a factory that can make dies. So the die, they're picking out, they cut it, after that they do the packaging. Okay, so inside is a die, all your CMOS, NMOS, PMOS inside. Then here, there we have the connection, right? Terminals. All these terminals will be connected, so they will solder here. So after that, it becomes the processor, right? Microprocessor or any of the IC. Yeah. So this one inside we call it die. But before it become die, it has something round in shape. We call it wafer. So the wafer is round in shape. So when they manufacture one wafer. After that, they cut it into many dies. They cut like this. They cut. Okay, they cut. But the problem when they cut the wafer, so this one is a wafer. What happened? Because the IC is square in size, but the wafer is round in shape. So you see, I cut. Okay, this one have to throw. This one I have to throw, right? Here, this die I also have to throw. I have to throw many. Then only I have 9 of them working for me. Okay, so when they do the IC manufacturing, so many of the parts here will actually spot already. So one other problem is inside the wafer, there might be some defect. Okay, we have the defect here. The defect can happen anywhere inside the wafer. If let's say the defect happened here, so the 6 die actually already can throw away already, right? So at the end, one wafer originally you see it can be cut into many dies, right? But now, due to some limitation like the side problem and also the defect at the middle, so you can only have certain number of the dies. So this one you call it U, die U. Okay, the die U is given by the formula wafer U multiply 1 plus defect per unit area multiply die area and also the alpha, where the alpha is the current technology. So sorry for that because my formula here is not very yes, here is quite blur, right? So I have already made another, we have already made another slide discussing same formula here. So you can see that the cost of IC, what is the cost of IC? The cost of IC actually equals to cost of die. What is the cost of manufacture one die and the cost of testing the die, plus the cost of packaging and final test. And we have the final test yield. So the cost of die equals to cost of wafer divided by dies per wafer multiplied die yield. And the dies per wafer equals to the area of the wafer minus the defect, the site, all this wasted area. Don't worry, when we do the tutorial, you'll use all these formulas. Also, the die yield is given by this formula, where the alpha is actually today's energy that will give it to you, and the defect density is 0.4 to 0.8 per cm squared. Okay, so these are all the formulas. Okay, so without further ado, so I think it's cut. Okay, it's short. So I think from now, I should give you a little bit exercise, right? Will I be able to give you exercise? Okay, because your friend has already done this for the, okay, we will change the number here. So now, find this one not 300, and make it into 500 millimeter, okay? And also 50, 50 cm for die that is 2 cm, 2 cm on the side. So this one is actually diameter. Sorry, that day they say it's not really it's a diameter. Okay, so find the die yield for the dies that are 1.5. We will just do this one first. Okay, we do this one first. The other question we left it for the tutorial. Can anyone pick out a piece of paper? Then later you can share your answer. Usually I will use a Jamboard. Yeah. So I give you 5 minutes. You do this using the formula inside your lecture notes. Yeah. So this will be the formula. Number of die. Number of die per wafer equals to this. So use this formula. Yeah, and do this. Later, please share your answer at the Jamboard. Now I go to create a Jamboard so everyone can go and share your answer. Okay, I'm going to share you the link, a copy, and I will put it at the chat box. So you can click this chat box and then try to join the Jamboard class exercise today. Okay, see Young Wen Liang already joined. Ernest, many have already joined. Yeah? So you can put the answers inside this Jamboard. You can write it at the Jamboard after you have finished. After you finish, then only we go for rest. Remember the 50 cm is actually a diameter. Yeah. So how many dies you can generate from the factory? Yeah. So you substitute into this formula. Die per wafer, pi wafer radius. So let's say here, say diameter, so you have to divide by 2, right? Radius. And the die is square. So anyone? Let me see whether you have already finished. 1907. And you can click the Jamboard link at my chat box. So then we can write. Anyone have already finished, you can write your answer there. For Jingwen, are you writing answer? Yeah. Or you want to directly scribble also can. No problem, just use the mouse if you can. Write on a piece of paper first, or you can actually take a picture and then after that you have the image there is okay. If you, let's say you want to take an image, 490. How many? 490, yeah? You calculated, you get 490. Can you give me the steps as well? Just everyone want to see how you get the 490. For your information, this formula is actually an estimation only. It also depends how people come. Okay. Sometimes I get a little bit more. Depends on some technology also. Yeah. So you can actually join. Yeah. So you click here, and there is a yeah. So you can click this Jamboard, and then you can go to the Jamboard. 490. Is everyone getting the same answer? Yes, sir. So, okay, very good. So how do you get the 490? Can you show me the steps? Do you have the step? You can actually take a picture. After that, you add the image. Take a picture, add the image, and put it here, your work. Or like me, I can use a pen because I have a pen. I have a digital pen. Yeah. Okay. Yeah, you get it. 490. So everyone get it. So Jay is Paul Wen. Okay, thank you. So very good. This is a big report to Wen. Okay, very good. 490. We just round to the nearest number because it's just an estimation. So now it's already 2:53. So I think we will rest for 15 minutes so that you can rest a little bit before we go into the performance session. Then we will learn a little bit about performance and then we'll do some exercise. So from now, I will let you to have some rest. You can go and have a little bit tea time at home now, of course. So then we start again by 309, 309. Okay, or 310, 310. So I will see you later. Okay. Any more question before we end the first session? Yeah, sir. Can sing? Yeah. Can sing? Yes. Any question? Can I have the classroom invitation code? Oh, of course. You haven't come in yet. Oh, it's you lah. Okay. Yeah, of course. I will give you now. Classroom. The code is, where's the code? This is the code. Let me give you the code. Wait, so I copy the invite. Copy invite. Have I copy? Okay, now go to the meet. Put it here. So you can join, can sing. Okay, all right. So I will see you. 15 minutes later. 3:10. 3:10. So have a good rest. Then later I will continue to discuss. Thank you. So good afternoon, class. I think 10 to 15 minutes has passed so fast, right? So it's time to study again for our subject. Good afternoon, Yao Ting, Long Yao Ting. Okay. So we are going to continue. So I know the time passed very fast, right? We never realized that it has passed, right? Then we have to come back to the class again. So we'll continue. Can everyone hear my voice clearly? If yes, then I will just continue, yeah? So let us look at the performance trends about the bandwidth over latency. So what are the difference? What is the difference of the bandwidth over the latency? In computer, we have two performance measure that we need to perform. One is the bandwidth, one is the latency. Bandwidth is also called the throughput, means how the total amount of work done in a given time. For example, if you are given a computer, so let's say you want to, let's say you can key in 10 documents in 1 hour. So this one is your throughput, okay, or your bandwidth. Yeah, 10 documents in 1 hour. So such as megabyte per second for a disk transfer. Let's say if your USB can transfer 1 gigabyte per 1 minute, so that one is your throughput. Okay. How about the latency? The latency or the response time is the time between the start and completion of an event. For example, let's say if you want to do the disk access, you can access this within a few milliseconds. That one is a latency or response time. This one is calculated in how much work. This one is calculate how much time, 2 nanoseconds. So of course, for the how much work, the amount of work, the bigger, the better, right? So for this one, the shorter time, the better. So you can see that the relative bandwidth improvement and the relative latency improvement has been increased throughout the years. So you can see that the memory has already have higher bandwidth and also shorter response time. So same goes to the microprocessor and also the network card, your Wi-Fi your Wi-Fi nowadays has become faster and faster. Last time when the internet was first invented, they're using modem. So this modem, you have to connect to the telephone. So when you connect to the internet, so you hear the voice, that only you are able to connect to the internet. So you can ask your parents or your brothers, sisters about this. So maybe they have already go through this stage. Okay, they connect through the modem, and then you can connect with the speed of 56 kilobits per second. It's very slow compared to nowadays. But nowadays, at my house, my modem can have 100 Mbps per second. Okay. So previously, when you use the telephone, it's only 56 kilobyte per second. Okay, so there are a lot of improvement within 20 years. Okay, so the latency improvement also same. It has improved over the time. So we also want to talk about the silicon wafer and the dice. So there is an exponential cost decrease when the technologies is basically the same. So basically a wafer, this is a wafer, it's a piece of silicon, okay? A wafer is a piece of silicon and is actually manufactured. After that, they're manufactured using some technology. They use some light technology, ultraviolet light technology, then they use the silicon and make this wafer. I believe you have already studied this in digital electronics. A wafer, after that, it will be tested and then chopped into dies. Okay, and this dice is actually the IC. It is the main component of the ICs that are big. So the die, when you cut it out, so you have package here. Okay, the package, then you can solder it into the die. So this is how you make an IC, okay, in the factory. So this wafer basically has some limitation because you can see this die is already spoiled. This die also spoiled, right? Because you can see it's at the edge, right? And also this one also spoiled. So you can see at the side, there are many dies along the edge and the dies, okay? You see the dies along the edge of the wafer. So this comes from the AMD. For those who haven't known yet, in the computer processor manufacturer world, there are two very important manufacturer for the system technology, for computer technology is Intel and AMD. Okay. So we want to study about the response time, throughput, and performance. So response time, we want it to be as short as possible. For the throughput, we want it to be as high as possible. And performance, of course, we want it to be as high as possible. So the response time means this is the time between the start and also the completion of an event. Also referred to as execution time. Let's say if you start the Word program, it takes like, for my computer, maybe it takes like 5 seconds. So this will be the response time. So for me, as a computer user, I'm very interested in this time because I want to see when I click the Microsoft Word, how fast will my program appear? Because if I click after that, it appears after 1 minute, then it will waste my time, right? I might need to do my document fast. And also it's very important to me, so I'm very interested. Okay, so second one is the throughput. It's the total amount of work done in a given time. Previously, when I start my online class, so my computer, my Unify, I only subscribe for 30 Mbps. After that, I found that the performance is not good and the quality of the video and the sound is not good. So I upgrade to 100. Okay, I have no choice but to upgrade immediately. Okay, within a few days, then I get higher throughput. So with this higher throughput, I'm able to do the video conferencing. Okay, so this is about the throughput. So in comparing the design alternative, so when we say computer A is faster than computer B, or computer B is faster than the computer A, how do we measure it? Okay, or we say this Unify is better than the other Unify. How do we measure it? So we can measure that using the number of times faster, number of times faster is equals to the execution time for the Y, for example, 100 Mbps over 30 Mbps, megabit per second. So I have 3.3 times. Sorry, this one is time. Okay, we go, this one, let's say you want to throughput is this. Let's say you have a time. Okay, time. Let's say we give the time. So let's say this one, I use a 100 second. And this one I use, not right. This one I use a 300 second. Let's say 330 second. Okay, 100. I think I have to reverse, right? Okay, sorry. So 330 seconds, and this one is 100 seconds. So I can say that the X is faster than Y by 3.3 times. So the N is 3.3 times faster. So you can see that the phrase X is faster, 3.3 times faster than Y is used here to mean that the response time or the execution time is lower on X than on Y. That means if I use the X, I will get it faster because execution time is 100 seconds, whereas for the execution time for Y is 330 seconds. So we already studied the execution time, where the execution time is actually reciprocal. Reciprocal means 1 over something, right, of the performance. So when we say execution time is, let's say, 10 seconds. So the performance, let's say here we have the execution time. Performance is 1 over execution time. That's why the N equals to execution time Y over execution time X equals to 1 over performance Y. Because the performance will be equals to 1 over 10 equals to 0.1. Okay, if let's say you have the 1 second, then the performance will be 1. So in this case, when the performance number is higher, then it will be better. So here, you will get the new formula. So N equals to execution time Y over execution time X equals to performance X is, observe this. The Y and X is interchanged, okay, over the performance Y. So in this case, you will be able to calculate how many times this computer has the better performance than the other one, okay, by measuring the performance. Let's say this one is performance is 10, the other one performance is 5. So you can see that there are 2 times better, right? So now, in order to measure the performance, we use the user CPU time. Response time, when we talk about response time, we start a Word document. It will include the disk access, memory access, input output activities, CPU events, and operating system overhead, and everything, including when your friend WhatsApp you, then suddenly take in some of your processing power, right? Or sometimes when you browse the internet, then your friend call you, then the telephone have to take care of this telephony function first, right? So all this will include inside the response time. So in order to get an accurate measure of performance, we use the CPU time instead of response time. What is the CPU time? CPU time is the time the CPU spends computing a program and does not include time spent for input output and running other programs. So CPU time, if you know Unix programming, so you can type in the time. So you can type time, this command in Unix or Linux. So you get this 90.7, 12.9, depends on the your computer, 2 minutes, 39 seconds, and 65%. So all this represent the user CPU, system CPU, total response, and also percentage. So you only use the first one. 90.7 seconds is your user own time, where the 12.9 seconds is used by your operating system, which is Unix or Linux. In our performance measure, we use user CPU time because of its independent on the OS and other factors. So there are some quantitative principles of computer design. So when you want to design computer, there are 4 things that you must consider. So first thing is, if you want to improve the performance, take the advantage of parallelism. For example, let's say you have one processor, you want to improve the performance, give another few, then the performance will be increased, right? Let's say you have one unified, right? One modem, then you subscribe another one, then you get a better performance. Another one is a principle of locality. For example, let's say you design a computer, a motherboard here. Let's say this is the motherboard. Okay, motherboard. You know what is motherboard, right? is inside your computer. Okay. Then here you put your, let's say this is a microprocessor. Okay. So where do you want to put your cache? Of course, you put it as close as possible. Let's say cache is here. It's faster. So principle of locality say that the nearer you put the cache, anything nearer, then they will be faster. Okay, they will be faster. After that, then put, then after that, they put inside lah, even faster, right? Directly inside the processor. Okay, so this is about the principle of locality. The last one is focus on the common case. So you want to increase, you want to improve the power, resource allocation, and also the performance. So there is one very important law that you must know. If you don't know, then you never study computer architecture. It's the Amsterdam Law. This Amsterdam Law means say that the performance improvement should be gained from using some faster mode of execution is limited by the fraction of the time the faster mode can be used. So please remember this sentence, yeah, because this Amsterdam Law is very, very important. If you never learn this, so you haven't learned the computer architecture. So Amsterdam Law means that, for example, what's the meaning? Limit by the fraction of the time. For example, I improve multiple function, multiply function, improve the performance by 200%. Okay, but my computer will only do multiplication for 1%. Okay, of the work of the total work. Okay, so how much performance increment I can get? Let's say I increase this by 200%. So only this 1% of the total work will be increased by 200% performance, right? Let's say if this work take 100 seconds, okay, so I can only improve the only improve 1 second, right? And it become 0.5 seconds. So total, this one will be reduced to 99.5 seconds. So although I improve the performance multiplied by 200%, but I only can improve the performance of a fraction of the time the faster mode can be used, because all my other works using other function, not multiply. Okay, so that is the Amsterdam Law. Amsterdam Law means the performance gain that can be obtained by improving some porting of the computer can be calculated using Amsterdam Law. So Amsterdam Law defines the speed up that can be gained by using particular feature. Whereas the CPU performance equation means essentially all computers are constructed using a clock running at constant rate. This will be another method to for calculation. And CPU time then can be expressed by amount of clock cycles. What is a clock cycles? For my computer, my clock cycles, actually, for example, I have the 2.2 gigahertz on my laptop. Okay, it's my clock cycles. What's the meaning? I can run. My clock is actually 2.2 billion times per second. Okay, so let's say if I have okay, let's say I have 4.4 clock cycles that I need to run this up. So I only need 2 seconds, right? So this one only need, sorry, a billion. I only need 2 seconds, right? Let's say okay, 4.4, 2.2. So I only need 2 seconds to implement everything. So this one is, we use the CPU performance equation. Later, you have to do the exercise. So the Amsterdam Law means, say that the speed up is equal to the performance of the entire enhancement when possible over the performance from entire task without using the enhancement. Okay, so let's say here I have speed up its performance. What is the thing that I have? I have 99.5, right? Performance. Okay, here performance without using is 100. So the speed up will be this one. Okay. Alternatively, the speed up is execution time for the entire task without using enhancement, which is 100 seconds. Enhancement is 99.5. So this is my speed up. So I have very little speed up. So what is my speed up? Let me use my calculator to calculate. Later, when you do a tutorial, please make sure you know how to calculate. Yeah, I have a one. My speed up is very little only. 1.005 is half percent speed up. Okay, even though I spend all my time design a very complicated circuitry, and then I can improve my performance of multiplication by 200%. At the end, you only improve the whole system by half percent. Okay, so this is meant by the Amsterdam Law. Okay, so no matter what you do, you have to make sure the thing that you do is very important to a computer. Then only you can improve the overall performance. So Amsterdam Law is given by this formula. So execution time, this new execution time mu equals to O1, for our case 100 seconds. 1 minus fraction enhanced minus section enhanced is 1 minus 100, right? 1 minus 100 fraction enhanced 1% only, right? So fraction enhanced is also 1%, right? Okay, and then speed up. But speed up enhanced, so 1.005. So then only you can calculate the time. So after you calculate, then you should get the 99.5 seconds. Okay, so this is what is meant by the Amsterdam Law. So this one you also can do yourself when you do the tutorial time. Okay, so here I think we should go back to the tutorial question. So I will give you a little bit tutorial question, because if I talk too much, then you won't be able to understand. So because right now we are having the online class. Okay, let's do some exercise. Okay, so which one is answer? Okay, so third one. Okay, good, very good. So let's spend some time to understand this. Let me, Okay, suppose that we want to enhance the processor used for the web serving. So the new processor is 10 times. 10 times faster. Okay, so for example, I design a processor. After that, I enhance the processor used for web serving. There's a particular part inside my processor. Specifically, I want to improve it so that it can do faster web serving. So the new processor is 10 times faster on computation in the web serving application only than the original processor. So 10 times faster, wow, very fast. Okay, assuming that the original processor is busy with the computation 40% of the time, so means that 40% of the time, you will not be able to get any of the improvement. And it's busy with the computation, or 40% of the time you're busy with the computation. Okay, yeah, you will get the web serving faster, and it's waiting for the I/O 60% of the time. Means that you wait for the user to ABC, is still wait 60% of the time. So what is the overall speed up gained by incorporating the enhancement? So I want you to spend 5 minutes to 10 minutes to do this question by, okay, let me clear this first. Okay, so wait, I will, you can use back the same Jamboard later, just now. Okay, so Okay, so now I want you to use this formula to calculate what is the overall speed up. What's the overall speed up? But before you can calculate this, you need to use the previous formula, right? Speed up here. So let's calculate this, and then can you see my computer? If not, then please download the lecture notes. I'll give you 10 minutes until 3:45. We'll do this question. Don't worry, on Friday we still have 1 hour, right? Now we can finish the chapter 1 by Friday. Yeah. Suppose that we want to enhance the processor. This for web serving. Yeah. So go back to the Jamboard that I have already given to you. Return to the second page. Yeah. Then after that, I'll write your answer there. I think this one quite complex. Yeah. Any question, you can let me know. Jamboard, we go to the second page. Yeah. Second page already. Who did this? Wafer diameter. I don't know who write this. Who did this? Okay, turn to the page number 4. Yeah. Number 4. Yeah, who wrote the 3 for me? Thank you. So I wrote the answer here. You spend some time on your paper first, then you write over there. First, you need to calculate what is the mean time size. Okay. If you can actually assume, let's say you assume total is 10 seconds. Then after that, 4 seconds used for computation, 6 seconds used for I/O. Then it's easier for you for calculation. If you don't want to use some variables. If you have any question, you can turn on your mic. Just I already marked all your attendance. If anyone attend, but I haven't marked your attendance, let me know. The fraction that you can improve is basically 40% only. But this 40%, let's say you have 4 seconds, you can improve it become 0.4 seconds, right? That's 10 times faster. Then you calculate the overall performance and speed up. We turn to page 10. Yeah, we turn to page 10 of your Jamboard. This Jamboard will exist forever. So you can download the link. You can copy your link in case you want to come back. You can see this link again. So I won't delete it. You exist there forever. Okay, first question 435 correctly. Second question is start from page number 45. Speed up. I only input output because most of the time the computer is waiting for the user to key in something, right? Even though it can be very fast, but you have to wait for the user to key in first. That's one of the bottleneck a computer can face. Chung Yi is writing, right? I see Chung Yi writing at page number 5. Speed up over 1 over 1 minus fraction. Fraction enhanced is 0.4, right? 0.4. 0.4 here, and also speed up. Well, speed up enhanced is speed up for the enhanced is 10 times, right? Yeah, so you calculate and then see what is the answer. Let me check the answer, yeah? Solution 1. If you have the answer, then you can do it more confident, with more confidence. 1.56. Okay, answer is 1.56, yeah? If you get it, you write the answer at the Jamboard. Yeah, so replace speed up overall equals to 1 over 1 minus 0.4, and then 0.4 over the speed up 10. You see whether you get this. Yeah. Okay, now I turn to the Jamboard, yeah? So you can refer to your yeah, I see Chung Yi is writing, right? Yeah. So we have, yeah, Chung Yi, sorry, calculator is 0.64, 1 over 0.64. 1.56, correct. Execution time for current execution time is 0.64 times and the speed up overall. Speed up overall, you have to use this one. Chong-Yi, you have to use this formula. 1 over 1 minus fraction, this 0.4, then only you will get. You want to have the speed up, means it's 1 over execution time. Speed up is 1 over 0.64. Yeah. You will still get that, but you can use different formula to calculate. Yeah. So Chong-Yi, you have the pen, right? You have a pen, right? Writing pen, or you use the mouse. Some people can use mouse to draw, but I cannot. I have to use the pen like this. You can 1.6 5625. Yeah, very good. Yes, very good. Okay. Oh, Yan Chang. Okay, Yan Chang, thank you. Very good. Very good. Yan Chang, because the symbol is Yan Chang. Okay, so Yan Chang. Oh, the symbol is very similar. Okay, very good. Give a big round to Yan Chang. So for your information, you can see that basically, okay, this is my pen. Okay, pen. Okay, so if you, this one is also equals to 1 over execution time. Okay, 1 over execution time. So this one 1 over 0.64. Yeah, can't think. 1 over 0.64. Okay, this one also 1 over 0.64. You will get the exactly same answer. Yeah. So very good. Since we see the time, I want you to question. Let's see. This one you have the answer already. So let's try this. Question number 4 is also calculating the speed up. Okay. Yeah. Question 4. Okay, so I think this one we can do. We still have 10 minutes. You have a system that contains a special processor for doing the floating point operations. Okay, you design a new special processor, a core processor that do floating point operation faster. You have determined that 50% of your computations can use the floating point processors. So that means overall, 50% of your calculation will be based on floating point processor. So you have done the speed up 50 times, 15 times. Okay, that is a very good improvement, right? That's why some people will have a max processor, floating point processor, graphic processor, because they want it to be very fast for certain portion of the computation work. So calculate the total overall speed up. Overall speed up. So you can start to do already. Then I will see you in Jamboard. Jamboard. So 1 over 0.64, you get the same answer. Yeah, thank you. Okay, okay. Yan Chang, so Yan Chang, thank you. So we go to the next page, and then you can write your answer for the next question. This one, I think you have already have the formula, but never mind, I can give you if you don't have. Yeah, so this will be your overall speed up equals to, so you can start to do. Then after that, yeah. So this one, please do this. Then you, write your answer at the Jamboard. So I give you like 10 minutes to do. Yeah. 8 minutes. Yeah. Yes, we have almost 4 now. Question 4. %, speed up 15 times is very good performance increase. Calculate the overall speed up. What's the formula? Second formula here. At your left hand side, second formula. Speed up overall equals to 1 over 1 minus fraction enhanced plus fraction enhanced over speed up. And the second question, calculate the overall speed up achieved. We modify the compiler so that 75 of the computation. Well, this time they want it to be even more thorough. So 75%. Then third one, what fraction of computation should be able to use a 35 processor in order to achieve overall speed up of 2.25? So you just manipulate the formulas. Second one didn't have the answers, but I believe you are confident already. Just calculate. After you've done a few times, then this one is just Amsterdam Law. It's just very simple way, right? Follow the formula. On Friday only, we will study the clock cycles and then do a few examples. Then you will be very good in calculating the performance of a computer. Then you understand why you want to buy a higher clock rate for a computer, right? Have you done? Is this blue color is who? Fraction enhanced 75%. You can cooperate with each other. 1 do 3, 1 do 1, then you'll be faster. Yan Chang still doing. Yeah. Okay, very good. 3, this is 3. 4. Okay. 1.875. Answer? Okay, very good. Thank you. Very good. Okay. Okay, let's do a big round of to encourage him. Yan Chang, yeah. The second one. You want the question, right? Question, sorry. Second one is 3.33, like you can calculate. 75%. This one 0.75 already. Yeah. Who gives clap hands? Picture. Zero point 0.75 Then not 0.7, 0.75. Yeah. Okay, very good. Take a pair of 3.33. Yeah, that's correct. Last one. Last one, they want 2.25, the speed up. So speed up equals to something, then you want to see what is the fraction. Then you have to do some manipulation of formulas. 2.25 here. So it's roughly 60%. Let's see this bigger a bit. You still have 2 minutes. Do you still have the class later? So on Friday, we will calculate the clock rate. We will learn clock rate and then we do a few exercise. What's the clock rate? What is the clock rate per clock cycles per instruction? All those concepts. So then you know why you need higher clock rate. But you see, nowadays the new computer, the clock rate can no longer increase a lot. The physical limitation has already reached there. Yeah, physical limitation already reached there. That's why they now use multi-core, use other, they will improve other areas. Yeah, clock rate already have a meet the bottleneck limit. Okay. Okay, very good. What's the number? What's the number here? X 2.1. Okay, let's see the answer. Yeah. Okay, what's the answer? The answer is 60%, right? Just now you said 60%. It's 60% not. Okay, very good. Please give a big applause to your friend, 60%. Yeah, 60%. Yeah. Okay, I think we have already done this. Very good. Yeah, who gives this? I cannot see. But never mind. So very good. So we will end our class here. So on Friday, please continue. We will study the clock cycles and other performance measures. So thank you very much. So anyone from this class got any question? Do you have any question that you want to ask me? For your information, I will put the recorded lecture in the Google Classroom. In case you want to listen back, you can listen a bit. Okay, no problem then. Thank you very much. It's now 4:01. Yeah. So all the best. If you have any question, you can ask me through the WhatsApp. Okay, thank you. Okay, thank you, Yu Yang. Thank you, Xu Pian. Thank you, everyone. Yeah, Maylin, Yihang. Yeah. Okay, so, okay, thank you. Bye. Okay, please study. Yeah. Okay, next week only we discuss about assignment. Thank you.